All right, how is everyone today? Everyone being 5 people, I guess. All right, any questions? We're gonna start a new topic this week, but any questions before we start? All right, so we're going to talk about counting. Um, and this is one of these topics in discrete structures that probably sounds pretty obvious, and we're going to start with things that we're probably familiar with, but we're going to build this topic into some possibly surprising, unexpected results. And so counting is 1, 2, 3, 4, 5, right? Big deal. We're done. A lot of what we're going to do with counting is we're going to try to count, say, the number of ways certain things can be done. And this will lead us into concepts like combinations and permutations and number of ways we can arrange things and so on and so forth. And we've encountered this, already a few times in this course. For example, when we talked about the power set of a set, the power set is the collection of all subsets. Well, if I have a set like, A, B, C, and I want to form subsets, one question is, how many different subsets are there? And, I can start forming sets. Here's a set. Here's another set. Here's another set. And so on. How many such subsets can I come up with? And we saw a rule for a finite set. If a set has, say, n elements, the power set contains 2 to that number of elements. But how do we know this is true, right? Well, we saw an inductive argument supporting it and so on. But it's a counting argument, right? We can ask the question, how can we enumerate the collection of subsets? And one way to think of that is, how many different ways can I choose some collection of A, B, C? Or perhaps, I can write down A, B, C, and if I'm going to include this in my set, I'll put a check mark next to it. And if I'm not going to include an element in my set, I'll put an X. And so the set AC might look like this. And so how many different ways could I put, check marks or X's next to these 3 letters, these 3 symbols? And that's a counting argument. So we're going to talk about a few different ways to count or enumerate collections of things, and we're going to tie it back into this idea of combinations of things or permutations and what exactly those mean. So let's begin with something called the product rule. And also, like most things in this course, unrelated to the product rule from calculus. So no DTs anywhere in sight here. Product rule works like this. Given a procedure P that can be accomplished by performing 2 subtasks. So I'm going to have 2 tasks, T1 and T2, in that order. So we're starting with some procedure, something we want to do. And we're told that we can accomplish this procedure by performing 2 tasks, T1 followed by T2. So for example, trying to sit 2 people in a restaurant. That's the procedure P. We can accomplish that by first sitting person 1 somewhere in the restaurant and then sitting the second person. So T1 would be the task of sitting the first person. T2 would be the task of sitting the second person. And if we accomplish T1 and then we accomplish T2, we've accomplished our original procedure, which was seating 2 people in this restaurant. So that's our setup. I'm going to close this shade. All right. Given a procedure P that can be accomplished by performing 2 tasks in succession, T1 and T2, if T1 can be performed a total of N1 different ways, and T2 can be performed N2 ways, then the original procedure P can be performed N1 times N2 ways. That's the product rule. So if some procedure can be broken into 2 tasks that you're going to perform one after the other, if you take the number of ways you can do the first task, multiply by the number of ways you can do the second task, that tells you the number of ways you can do your original procedure. All right, that's the whole product rule. And I want to look at a bunch of examples of how we use this to describe the number of ways we can perform some procedure by breaking it into subtasks. And the challenge sometimes will be figuring out what these subtasks are and then figuring out how many ways each of those can be done. And then we just multiply them, and bingo, we've got our answer. So, example. Suppose you have 3 people and you have a room with 20 desks. Let's say these 3 people are taking a makeup exam. So they're going to sit somewhere in this room of 20 desks, and you want to know how many different ways can these people be seated. So 20 desks, you're not allowed to share a desk with anybody. And so we can break this into 3 separate tasks in this case. So task T1, sit the first person. Task T2 will sit the second person. And task T3 will sit the third person. All right, so here's the questions now. How many ways can we accomplish task T1? How many different ways can we sit one person in a room with 20 desks? 20 ways. All right, after we've accomplished T1, now we're going to do T2. And so how many ways can we accomplish task T2?
19.
Only 19 ways, because we've already done T1, we've sat one person at one desk. There's only 19 desks available now. So task T2 can be done a total of 19 ways. And then finally task T3, sitting the third person. Well, we've already sat 2 people. There were 20 desks, now there's only 18, but they can sit at any of those 18 desks. And so if we multiply these, that's the total number of ways we can sit 3 people in a room with 20 desks. And that's all there is to it. So let's look at license plates. And this is a license plate in Smallville, USA. So there aren't a lot of people there, and a license plate consists of 1 letter plus 1 digit. And so how many possible license plates are there? Well, we can phrase that question in terms of how many different ways can we pick 1 letter followed by 1 digit? Because each license plate corresponds to a letter followed by a digit. So our procedure P is the procedure of picking a license plate. And we can break that into two subtasks. T1, choose a letter. T2, choose a digit. So how many letters do we have to choose from? 26, A through Z. And if we're allowed to pick a single digit, there's 10 digits, 0 through 9. So the number of ways we can complete task T2 is 10. And the product rule says take their product, that's 260. That's how many ways we can choose a letter followed by a digit. That's how many ways we can choose a license plate. That's the number of possible license plates. Is this making sense so far?
Simple enough.
Okay, good. All right, we go out to lunch. And you're going to get soup and salad. And there's a total of 3 soups and 5 salads that you can choose from. So how many different lunches can you have?
Uh, 15.
Yeah, 15. So the procedure of picking a lunch is 2 tasks. Task 1, pick a soup. Task 2, pick a salad. Number of ways to pick a soup is 3 because there's 3 soups. Number of ways to pick a salad is 5 because there's 5 salads. Multiply those. 15 ways to choose a soup and a salad. 15 different lunches you could have. All right, so let's look at some more computer science relevant examples. So suppose you have a 4-bit number. Boom, 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 boom. There's 4 bits. And we want to know how many 4-bit numbers are there. So how could we take the task of creating a 4-bit number and break it into a set of subtasks? What could our subtasks look like?
0s and 1.
Okay, can you put it in the... That's correct. Can we put it in the terms of a specific procedure we're going to ask someone to do? And it's strongly related to 0s and 1s.
A 4-bit number would be a number with a 1 as the most significant bit, right?
It does not have to be a 1. It can be any combination of 4 1s and 0s.
Oh, I see. Okay.
So yeah, we can have leading 0s, unlike decimal numbers.
We'll look at the number of spaces, and then the number of digits possible in each space.
Okay. So we've got a room full of people ready to do our bidding, and our task is, I want you to give me a 4-bit number, but we want to break it into a set of smaller steps because we don't know how many ways we can get a 4-bit number. So we want to break this into simpler subtasks. In the spirit of what we did here. Yeah, go ahead.
It should be 15.
Yeah, but let's think about subtasks. That's the right answer.
Would it go bit 1 is either 1 or 0, bit 2, 1, 0?
Okay. So task T0 let's pick this bit. Or let me just call this task T1. We're going to pick this bit. Task T2, we're going to pick this bit. T3, we're going to pick this bit. And T4, we're going to pick this bit. If you perform those 4 tasks, you will end up having created a 4-bit number. And so the process of choosing a 4-bit number can be accomplished by performing these 4 tasks. Choosing this bit, this bit, this bit, and then this bit. So we've broken our original procedure P, creating a 4-bit number, into 4 subtasks, T1 through 4, where each of those subtasks says, let's pick 1 bit. And so how many ways can we accomplish task T1? How many ways can we choose a value for this bit position?
2.
2. We can put in a 0 or we can put in a 1. That's what a bit is. It's a binary digit, which means it's a 0 or a 1. And task 2, similarly, there's exactly 2 ways we can accomplish that. We can put in a 0 or we can put in a 1. And task 3, there's 2 ways. And task 4, there's 2 ways. And so the product rule tells us the total number of ways we can pick a 4-bit number is just the product of 2 times itself 4 times. That's where we get the 16 from. Which, by the way, is 2 to the 4th, because, you know, we had 4 of these things to multiply together. Just for kicks, if we had a 5-bit number, how would this analysis change? How would we calculate the number of 5-bit numbers?
Add T5.
T5, pick the 5th bit. And the number of ways to do that would also be 2. And so our total number of ways to do this would be 2 times 2 times 2 times 2 times 2, which is 2 to the 5th. And if we wanted to do this, we could show that the number of 6-bit numbers would end up being 2 to the 6th by exactly the same argument. We just have to add, you know, another task, T6. And so we could form a proposition that the number of n-bit strings is 2 to the n. So I could say P of n is the proposition that the number of n-bit strings is equal to 2 to the n. And we just, you know, showed that P of 4 equals 16. So that's true. So how could we prove P of n for all n, say, bigger than or equal to 4? What technique might we use? Just a wild guess.
Induction.
Mathematical induction. Anytime that we have something that we can, you know, confidently say, hey, I could keep doing this. I could show that there's 2 to the 10th 10-bit numbers by just, you know, having 10 subtasks, and each one would be doable 2 ways. And if I multiplied all 10 of those, that would be 2 to the 10th, right? And then someone says, well, what about 11 bits, you know? And you go, okay, same thing, and you do it again, right? And then they say, well, what about 12 bits, right? If you want to avoid having to repeat this time and time again, but you can see how you could do that, that's when you can pull in mathematical induction usually. And you could construct a very formal proof by, you know, defining a family of propositions and then proving that you know, P of n implies P of n plus 1. and you got p of some base case, and put those together, and you can use that to prove p of n is true for all cases. So just keep that in the back of your minds. All right, so here's a counting argument that the number of n-bit strings is 2 to the n. And that's something, you know, that we see in Engineering 250, and we encounter it more and more in computer science. But it can be shown, you know, with this counting argument using the product rule. So let's continue in that vein, and let's think about a truth table. So consider a truth table of n variables. So, you know, I don't know, A, B, C, D, 4 variables. And so how many rows do we have in a truth table for a function of n variables? Well, each row corresponds to some different n-bit number, right? We write down all the possible, in this case, 4-bit numbers, and that defines the number of rows. And so the calculation we just did tells us that the total number of rows is 2 to the n. So now we can ask a slightly more interesting question. How many functions, how many binary functions of n variables are there? We know there's an AND, there's an OR, there's an XOR, there's a NAND, there's a NOT, right? These are all functions of 2 variables. For n variables, how many possible functions are there? And this is the same question as how many different truth tables are there for a function of n inputs. So if you have n inputs, you have 2 to the n rows, and the question is, how many different ways can we fill in this output column?
Wouldn't it be 60?
Possibly. Can we describe filling in this column as a series of subtasks? So what go ahead.
Would you pick a row first and then figure out which function you were going to use?
So pick a row and choose whether this is a 0 or a 1. Go to the next row, choose whether this is a 0 or a 1. Go to the next row, choose whether this is a 0 or a 1. If you do that for every row, you're done. You've defined a function. So how many different functions are there? The same as the number of different ways we can fill in zeros or ones in this output column. Right? Because if we have 2 truth tables with a different set of zeros and ones, it's a different function. And if we have 2 truth tables with the same order of zeros and ones, those are the same function. So the question of how many binary functions of n variables there are is the same as the question of how many different ways can we fill in this column with zeros and ones. And we can break that into a series of subtasks. We can have our first task, T0, which is to choose a 0 or a 1 here. T1, which is to choose a 0 or a 1 here. T2, let me start from 1. T1, T2, T3, which is to choose a 0 or a 1 here, and so on. And our last row will be T2 to the n, choose a 0 or a 1 here. And the number of ways we can do each of those is 2. And so the product of these is going to be 2 raised to the number of subtasks, which is 2 to the n. That's the number of possible functions for a binary function with n inputs. So if you have 2 inputs, 2 to the n is 4. So you have 4 rows to your truth table. 2 to the 4 is 16 possible functions of 2 input variables. So and, or, NAND, NOR, XOR, XNOR, there's 6 of them. There's apparently 10 more truth tables. The yup function and the nope function, there's 2 more. There's the wire function, whose output is just the same as the input, as one of the inputs, and so on. All right, so if n equals 3, so any 3 input gate, how many possible gates are there? Well, 2 to the n is 8, so the truth table for a 3 input gate is going to have 8 rows. And if we're trying to fill in 8 values, the number of ways to do that is 2 to the 8th, that's 256. So if you wanted to manufacture every possible gate of 3 inputs, you'd have 256 different gates. And if n equals 4, 2 to the n is 16, 2 to the 16 is 65,536. So 4 input gates, you got 65,000 different 4 input gates. So this is growing really quickly. If n equals 8, an 8 input truth table has 256 rows to it. The number of possible truth tables is 2 to the 256th. And that's somewhere on the order of the number of particles in the universe. So these grow quickly. But you can enumerate these all by just using this same product rule. So how many orderings are possible for a deck of 52 cards? So you got playing cards 1 through 13 for the number, and you got 4 suits, 52 cards total. Each card is different from every other card. And you're going to shuffle up the deck, and you're going to look at the order of the cards. How many different orderings are possible?
52 factorial.
All right, how do you know that?
Because it's you start with 52 possibilities for the first card, and then 50 more, and then
all right,
until you have one option.
Awesome. So we can break the question of ordering a set of 52 cards into 52 subtasks. Task 1, pick what the first card is going to be. Task 2, pick the second card. And so on. Task 51, pick the 51st card. And task 52, pick the last card. Where by first, second, third, and so on, I mean maybe, the position in the deck from top to bottom. Or the position, on a table from one edge of the table to the other. So first we're going to pick the first card and the second card and so on. The number of ways you can pick the first card is 52 because you haven't picked any cards yet. You got 52 cards in the deck. But once you've done task 1 and you've picked 1 card, there's only 51 cards left. And so the number of ways you can accomplish the second task is 51. The number of ways to accomplish the third task is 50 and so on. The number of ways to accomplish the 51st task, well, at this point you've already picked 50 cards. So you only have 2 cards left, and you can pick, this card or that card. You've got 2 ways to do it. And then the last task is to pick the last card. Well, that's the only card remaining. There's no choice you can make. You have to pick that card, so there's only one way to do that. And so the product of all of these is just 1 times 2 times 3 times 51 times 52, which is what we mean when we say 52 factorial. So this is where factorials start to come into these kinds of questions. And we're going to see these pop up a lot. All right, let's look at functions. Suppose f is a function from a set M to a set N. And the number of elements in the set M is little m, and the number of elements in the set N is little n. And we can say how many such functions are possible. How many functions can there be from a set M to a set N? So here's our usual picture of a function. There's M, there's N. Here's an arrow from M to N, and our function does what? It takes each point in M and maps it to something inside N.
M times N.
Something like that. So let's think about subtasks. The question of how many functions there are is the procedure of picking a function, right? So how many different ways can we pick a function? So let's think about how we can describe this process of pick a function as a series of smaller tasks that might be easier to enumerate. So to define a function from M to N, what could I do? What steps could I follow?
Pick a value or a point in M and map it to N.
Perfect. Pick a point in M and decide where it's going to go to in N. And then pick a second point in M and decide where that's going to go to. And pick a third point and decide where that goes to. And do that for all of the points in M. So we have a series of subtasks. T1, choose where some point M1 maps to in N. And so I'm going to assume my elements inside M. I can call these M1, M2, up to M, little m. So I'm just assuming those are names for the M elements. So task 1, I'm going to choose where M1 maps to. Task 2, I'm going to choose where M2 maps to. All the way up to task little m, which is where I choose where M sub little m maps to. And if I perform these M tasks, I will have defined a function. So how many ways can I accomplish task 1? How many different ways can I choose what value, say, this point M1 is going to map to?
N ways.
I can do it n ways because I can map this to any point in N that I want. If I don't put any restrictions on my function, how many ways can I then perform this task of choosing a point, say M2, choosing where that's going to go to in N? That's also n ways. And in fact, each of these tasks can be performed a total of n ways. And since I have m tasks, the total number of functions is their product. That's n to the m. So in general, if you have a function from one set to another, the number of possible functions is the cardinality of the codomain raised to the cardinality of the domain. Big number. But we get that from a counting argument. So just for fun, what if f is injective? So do you remember what injective means for a function? Yeah, so it's a uniqueness in mapping. It's saying that if m1 maps to this point, nothing else is allowed to map to that point. So now task T1, we can still perform that n ways, but task T2, we can't perform it all of those possible n ways because we can't map to this value here. We only have n minus 1 values left that we can map m2 to, and so this can be done a total of n minus 1 ways, and task 3 could be done a total of n minus 2 ways, and so on. And so you're going to get a smaller number. And it's going to look something like a factorial. We're going to come back to that in a few minutes and make it precise. All right, how many 3-digit numbers are there? Assuming that we allow leading zeros. So, you know, 007 will count as a 3-digit number. And forgetting what we might know the answer to be intuitively, the task of forming such a 3-digit number can be reduced to 3 subtasks. Choosing a digit here, choosing a digit here, choosing a digit here. The number of ways we can complete this subtask, choosing a digit right here, is 10. The number of ways we can choose a digit here is 10. The number of ways we can choose a digit here is 10. The product is 1,000. That's the total number of 3-digit numbers. Which makes sense because our 3-digit numbers are basically from 000 through 999. And there's 1,000 numbers there. All right, one more example of the product rule. Let's look at the number of elements in the power set of a set S. So this is the number of subsets of S. I'm assuming S is a finite set, so nothing weird. S is a finite set. How many different subsets are there? Well, that's equivalent to saying in how many different ways can we create a subset of S? And let me suppose that S contains n elements. And let me call these elements S1, S2, S3, all the way up to Sn. So there's the n elements in S. So my procedure I want to perform is to create a subset of this set. And how can I do that as a series of simple tasks?
take a value from S for S1, S2, S3.
Mm-hmm. And do what with it? I like that idea.
Create a new subset of it.
Okay.
Because
So a subset is going to be some collection of these, right? Could be all of them, could be none of them, could be some of them. And so we can think of this as a set of tasks. T1, decide whether to include S1 or not. T2, decide whether or not to include S2. T3, decide whether or not to include S3. All the way down to Tn, decide whether or not to include S sub n. And if we perform these n tasks, we'll create a subset. And any subset we come up with will be, a set that we would have gotten by a particular choice of choosing whether or not to include S1, S2, S3, and so on. And so performing these n tasks is equivalent to choosing a subset. Ergo, the number of ways we can perform these tasks is the same as the number of ways we can create a subset. That's the number of subsets, that's the size of the power set. And so once again, how many ways can we decide whether to include S1 or not? There's only two ways, right? We can decide to include it, we can decide to not include it. So task 1 can be accomplished two different ways. Task 2, exactly the same thing, can be accomplished two different ways. Task 3, and so on, all the way to task n. And then using the product rule, we multiply these n 2's together. Total number of ways we can form a subset is 2 to the n. So there's another illustration of the fact that the size of the power set of S is equal to 2 raised to the size of S. So that fact just keeps coming back. All right, second rule is the sum rule. So the sum rule works like this. If a procedure P can be done by either doing T1 or T2, then and T1 can be done N1 ways, same setup as before. T2 can be done N2 ways. Then P, the original procedure, can be done T1 plus T2 ways. So that's the sum rule. We've got another Engineering 250 flashback going on here, right? Procedures performed by performing this task and this task, we multiply. Performing this task or this task, we add. This is another rendition of, logical ands are somehow like multiplications or products. Logical ors are somehow like additions or sums. So products and sums, when we talk about sums of products and all that kind of stuff, same kind of harmony here. Same thing that we saw where when we do set operations, the intersection looks like an and, it's related to multiplication, and the union looks like an or, it's related to addition. This just keeps coming back again and again. So this is the sum rule. And if we have a procedure that can be done by either doing T1 or T2, The number of ways to do that procedure is the sum of the ways to do those subtasks. So for example, you go back to your restaurant and they've got 3 soups and they've got 5 salads. And you're going to order the discount lunch, which is a soup or a salad. And you want to know how many different ways can I order lunch? Well, you can break the procedure of ordering lunch into 2 possible subtasks. Task 1, pick a soup. Task 2, pick a salad. And you order lunch by doing this or doing that. The number of ways to pick a soup is 3. The number of ways to pick a salad is 5. 3 plus 5 is 8. That's the number of possible ways you can choose soup or salad. So that's the sum rule. And a lot of times we do combinations of these. So for example, suppose we want to pick a variable. So a variable is one or 2 characters. First character is a letter. Second character is a letter or a digit. So variables can be 1 or 2 characters long. First character has to be a letter. Second character can be a letter or a digit. And we want to ask, you know, how many possible variables are there? So is there a way to break this into a product rule or a sum rule? So the procedure is we want to pick a variable. We want to create a variable. So
could it be a product rule?
Could be a product rule. What would the product rule be?
Take a letter for your first character and then pick a number or a letter for your second character.
Okay. So T1, pick letter for first car. T2, pick letter or digit for second car. So the number of ways to pick a character is 26. Task 2 is to pick a letter or a digit. So how many ways can we choose a letter or a digit?
36.
So 36, which we can do just because we know there's 36, letters or digits. Or we could actually break that into a sum rule. We could say the task of doing this is a subtask of either Q1, which is picking a letter, or Q2, which is picking a digit. We can pick a letter 26 ways. We can pick a digit 10 ways. That's a total of 36 possible ways. So the number of ways to do this is 36. And so the total number of ways would be 26 times 36. Is that our final answer, though? Or why is that not our final answer?
That's just for numbers, isn't it? This is letter or numbers.
That's just for the 2-character version. But we can also have a variable that's just a single character. So if we have a 2-character variable, we can choose it this many possible ways. But it's possible that we could have a single character variable. And the number of ways we can have a single character variable is just the number of letters, which is 26 possible ways. And so we actually need to use the sum rule on this original procedure. To pick a variable, we either pick a 1-character variable or a 2-character variable. This is how many ways we can pick a 1-character variable. This is how many ways we can pick a 2-character variable. So the sum rule tells us the total number of ways we can pick a variable is the sum of those. 26 plus 26 times 36. So sometimes you break your problem and it's a combination of sums and products. All right, the last version of counting arguments is subtraction, or what's called the principle of inclusion-exclusion. And this is something we observed when we talked about sets. And we can write this as the following. The number of elements in the union of two sets, A1 union A2, is equal to the number of elements in the first set plus the number of elements in the second set minus the number of elements in common. So if we just do this, right, if there happens to be something that's in both of these sets, A1 and A2, we're going to count it once here and once here. But when we take the union, that element's only going to appear once, because sets don't have duplicates, right? So if there was one element in common between A1 and A2, this sum would be one number higher than the number of things in the union. We need to subtract that off. We need to make a correction for that double counted element. Subtracting the number of things in common would take care of that. So if A1 equals, A, B, C, D, E, and A2 equals C, E, F, G, number of things in A1 is 5, number of things in A2 is 4, but the union is going to be A, B, C, D, E, F, G. The number of things in the union is 7, which is smaller than 5 plus 4. The amount of times that we've overcounted, though, is just the number of things that A1 and A2 have in common. So what's in common between A1 and A2 is just C and E. And the number of things in common is 2. And so this is saying 7 is 5 plus 4 minus 2. So here's a question. How many 8-bit strings start with a 1 or end with a pair of zeros? So let's normalize. How many 8-bit strings are there? With no restrictions on any of those bits, except each bit is a 0 or a 1. So how many 8-bit strings? I'll take a formula if you don't know a number.
256.
256. Good. Awesome. 2 to the 8th. How many 8-bit strings start with a 1? Any idea how to find out? So if you have an 8-bit string that starts with a 1, it looks like this, right? And so how many binary strings can I write in this form? How many strings like this can I write?
2 to the 7th.
2 to the 7th. So how many strings like this can I write?
2 to the 7th.
2 to the 7th. That's 128. So a lot of these questions come down to sort of re-looking at the problem, thinking about it in a slightly different way. And if we think of, you know, a 8-bit string that starts with a 1, if we write it out like this, well, the only question is, how do we fill in these 7 bits? Well, that's just like writing a 7-bit string. So same idea, how many 8-bit strings end with a 0, 0? In other words, how many strings have this form?
2 to the 6th.
2 to the 6th, you got it. So there's 64 strings that end with a 0, 0. Because, you know, I've got an 8-bit number, these 2 bits are set, there's 6 bits I have to figure out. And how many ways can I do that? Well, that's just our 2 to the 6th, right? Same thing we've seen. So suppose, you know, set A1 is a set of strings that start with a 1. There's 128 of those. And suppose set A2 is the number of strings that end with a 0, 0. There's 64 of those. And my question is, how many strings start with a 1 or end with a 0, 0? In other words, how many numbers are there in the union of A1 and A2? And we know, you know, there's 128 things in A1, there's 64 things in A2, so we might be tempted to add those. But we know that's not going to give us the right answer, because the number of things in the union of 2 sets is not just the sum of the number of things in each set. We have to subtract anything that's in common, because there are some strings that belong to both A1 and A2. So we're going to have to subtract the number of things in the intersection. If a number's in both A1 and A2, what does it look like?
Starts with 1 and ends with 00.
It starts with 1 and ends with 00. You got it. So it has this form, and now the question is, how many different numbers are there in this form?
Maybe 2 to the 5th.
2 to the 5th, perfect. Because we've got 1, 2, 3, 4, 5 bits. So there's 32 numbers of this form. So the number of things in the union is the sum of the strings in this form plus the sum of the number of strings in this form minus the number of strings in both, which is 32. So this will be 128 plus 32. This will be 160. And that's all just counting arguments. All right, so let's take a break. When we come back, I want to go over the homework that that I graded and posted this week. I will grade your current homework, the induction assignments, sometime over the next few days. I'm not posting a new homework yet for the counting arguments because we're just starting counting today. So I'll probably post homework on Monday for this current unit. So, but I want to go over the homework. I forget which number we're up to, but the homework on number theory, I'll go over that after a break. So let's come back at in about 5 minutes. What are you doing, squirrel? Hanging around the corner of the shed, looking all innocent.
Oh.
What's that whiteboard? That arc welder.
beer. I'm trying to warm up.
Excellent. All right, we're back. Let me go over homework questions. So, first question was using modular exponentiation. So 2 to the 130th mod 7. And I think everybody who did this got it right. But if you didn't do it, or you weren't sure, modular exponentiation is this algorithm. We start off with 2 to the first is 2. And then we keep squaring our previous answer. So the square of 2 to the first will be 2 to the second. That'll be 4, 2 squared. And then we square that answer to get 2 to the fourth. This will be 4 squared, which is 16. And 16 is 2 more than a multiple of 7, so this is 2. And once you come back to a number you've already seen, you've got a pattern, which you can just follow. Right, I know 2 squared will be 4, I know 4 squared will be 2. And so we can fill in the rest of those without really doing a whole lot of work. And now we use the law of exponents. 2 to the 130th is 2 to the 128th plus 2, which is 2 to the 128th times 2 to the 2, which will be congruent to whatever this is congruent to times whatever that is congruent to. So 2 to the 128th is 4, 2 squared is 4, that's 16, which is 2 more than a multiple of 7. So 2 to the 130th is 2 more than a multiple of 7. And so we can calculate 2 to the 130th minus 2, that's this number right here. And if you do that number divided by 7, that's an integer. So you can sanity check this with a good calculator. All right, and then question 2 was to calculate 2 to the 6002, also modulo 7. And it wanted you to do this using Fermat's little theorem. I don't remember what number this homework was. This was the one that you turned in last Wednesday. So Fermat's little theorem tells you 2 to the 6th is congruent to 1 modulo 7. Alright, this is homework 6. Once we know this, we can raise this to any power that we want. And 2 to the 6th raised to the n will just be 1 to the n. And if we multiply 1 by itself a bunch of times, we still just get 1. So this is nice because we get this 1 over here on the right. We can leapfrog up to much larger exponents. And 2 to the 6th raised to the n, this is also 2 to the 6th times n. And so 2 raised to any multiple of 6 is going to be congruent to 1 modulo 7. Well, you're asked to find 2 to the 6002, but we can jump up immediately to say 2 to the 6000th is congruent to 2 to the 6th times 1000, which is congruent to 2 to the 6th raised to the 1000, which is congruent to 1 to the 1000, which is congruent to 1. That's Fermat's little theorem. You get that for almost no work. So there's 2 to the 6,000th. There's 2 to the 6,000th minus 1. If we divide that by 7, we get an integer. So this big number here, well, this original big number here, 2 to the 6,000th, that's one more than a multiple of 7. And, you know, trying to divide this by hand to see what the remainder is, you don't want to do that. But Fermat's little theorem gives it to us for free. So that's 2 to the 6,000th. We're trying to find 2 to the 6,002nd. So just multiply by 2 squared. That'll be congruent to 1 times 2 squared, which is just congruent to 4. All right, question 3, we were looking at modular equivalences. So remember, we have this rule, A is congruent to B modulo M, means M divides the difference of A minus B. So saying two numbers are equivalent mod M is the same as saying that M divides their difference, or their difference is a multiple of M, which is the same as saying that if you divide A by M and B by M, you get the same remainder, the same stuff left over. So answering these questions is a matter of looking at the difference and seeing if it's divisible by the moduli. So 26 minus 2 is 24, that is a multiple of 8. So this is true, these are equivalent. 13 minus 2 is 11, that is a multiple of 11. 13 minus negative 9 is 22, and that's a multiple of 11. So these are congruent modulo 11. Minus 5 minus negative 1 is minus 4. That's not a multiple of 3, so D is false. Minus 5 minus negative 2, that's minus 5 plus 2 is minus 3, and that is a multiple of 3. It's 3 times minus 1. And big number ending with a 7 minus 1,007, that ends up to be some big thing that ends with a 0. That's a multiple of 10. So all of these are true except for D. D is false. All right, and then which of the following numbers are prime or composite? So most people found these right away. 33 is composite, that's 3 times 11. 91 is composite, that's 7 times 13. And all these other numbers are prime. And worst case, you need to go up to about 10, so you need to divide by, we don't need to divide by 2 because these numbers are all odd. So you need to divide by 3, 5, and 7. And if your number is not divisible by those, you can say that it's prime. Because the next prime would be 11, and our numbers are smaller than 11 squared. So you only had to check 3 divisors. Right, the following is products of primes, so I think everybody succeeded in that. So 25 is 5 squared. 1260 is 2 squared times 3 squared times 5 times 7. And you know, the way you can do this is just start doing some division. Well, I was going to do it on my phone, but let me do it here. Right, so 1260 is even, so try dividing it by 2, you get 630. 630 is even, so try dividing that by 2, you get 315. So that gives you 2 squared times 315. Well, 315, I can tell that's divisible by 5 because it ends with a 5. So 315 over 5 is going to be 63 times 5. And 63, if I look at that, I probably know that's 9 times 7. And so I can write this whole thing as 2 squared times 3 squared times 7 times 5. And sometimes we order them in increasing order, but that's fine. And then 1024, you should recognize that as a power of 2. If not, you know, it's even. Keep dividing by 2, and you'll get all the way down to 1. But that's actually what 2 to the 10th is. And depending on whether you're a consumer or a seller, this might or might not be what 1K is. So 1024 is pretty close to 1,000. A K is technically 1,000. But is a kilobyte 1,000 bytes or is it 1024 bytes? It depends on your angle. And you know, 24 bytes out of 1,000, not a big deal. But if you go and you buy a terabyte hard drive and you mount it on your machine and you look at how many bytes there are, it's a lot less than a trillion. It's like 900 some billion, etc., etc. And it comes from this idea that this is used to represent a K. But if you're selling hard drives, you call 1,000 bytes a K. And so it's kind of a marketing thing. But anyway, this is a good power of 2 to know. 2 to the 10th is about 1,000, and you can use that to scale up, right? 2 to the 20th is approximately 1 million. 2 to the 30th is approximately 1 billion. So 2 to the 32 is approximately 4 more than that, 4 billion. So you got 4 billion 32-bit integers. And if you're doing 2's complement, cut it in half, plus or minus 2 billion. So that's your quick memory trick for knowing that 2 billion is the biggest number you can do as a signed 32-bit integer. So that's a good power to know, 2 to the 10th. 1025, though, really close but very different. But again, we know 1025 is a multiple of 5, so divide it by 5, and you get 205. And 205 is also a multiple of 5, so divide that out, and you get 41, and 41 ends up to be prime, so this is 5 squared times 41. Which is kind of interesting, because 1024 is just 2 to the 10th. And these representations as products of primes they don't seem to have anything to do with each other. That's my whole solution right there. Alright, and then Euclid's algorithm, didn't see a lot of issues with that. So I don't know, I'll just run through one of them. So let's do 1001 and 84. So the algorithm is right, 1001 is equal to something times 84 plus something. So how many times does 84 go into 1001? Looks like it goes in about 11 times, so it's 11 times 84 plus an extra 77. And now bring this down and bring this down and write 84 equals something times 77 plus something. And 77 goes into 84 once, and you've got 7 left over. And bring this down and bring this down. And so 77 equals something times 7 plus something. This goes in 11 times with 0 left over. And so this ends up being your GCD. And I think everybody did fine on the GCDs except for occasional math glitches here and there. All right. Any questions on that past homework? All right. Any questions on the homework that you just turned in, the induction homework?
Probably 3-4, number 3.
Which one?
3-4, number 5. There we go.
3.4, number 5. Oh, the factorial one?
Yeah.
Okay, so we want to prove this weird-looking formula: 1 times 1 factorial plus 2 times 2 factorial all the way up to n times n factorial is equal to n plus 1 factorial minus 1. All right, and we want to prove this using induction. And we want to prove this for, n bigger than or equal to 1. So, make a family of propositions. Now, to be totally formal about this, we shouldn't be using the ... We should be using a summation symbol. But I'm going to use the ... because I don't want to confuse the inductive part by worrying about rules of summations and so on. So I'm rewriting this. P of n is the proposition that this sum is equal to that expression. And my goal is to prove P of n is true for all n bigger than or equal to 1. And I'm going to do this using mathematical induction because that's what it said I had to do. So first step, I'm going to prove a base case. So I'm going to write out what P of 1 says. And P of 1 says, basically add up n times n factorial up to and including 1. So it says 1 times 1 factorial equals, and if n is equal to 1, 1 plus 1 factorial minus 1. Alright, well this is equal to 1, this is equal to 2 minus 1, which is equal to 1, and so, since 1 equals 1, this is true. So P of 1 is true. So our remaining step is to prove that if n is bigger than or equal to 1, P of n gives us P of n plus 1. Again, we're not trying to prove P of n is always true. We're going to say, if you tell me P of n is true, can I show you that P of n plus 1 is true? It's a much simpler task than trying to prove that P of n is always true for all possible n. In fact, in this step, we're not proving P of n is ever true. All we're proving is that if this is true, then that is also true. But by itself, we're not actually proving that any of these individual propositions is true. So this is a simpler task, which is why induction is such a powerful tool. All right, so here's our proof. Step 1, we're going to write P of n. That's our hypothesis. Step 2, I'm going to write out what that tells us. It tells us the following: 1 times 1 factorial plus 2 times 2 factorial plus n times n factorial equals n plus 1 factorial minus 1. That's the definition of P of n. All right, now I'm going to go to my ignore. And I'm going to peek ahead and think about what I'm after, right? I want to show P of n plus 1. Well, if this is what P of n says, what does P of n plus 1 say? It says that the following is true. It says that if I add up the first n plus 1 terms like this, I should get, instead of n plus 1, n plus 2 factorial minus 1. That's what I'm after. If I can start from here and do some stuff and eventually show that this is true, I am done. Because then all I have to say is, hey, since this is true, P of n plus 1 is true, therefore Pn implies Pn plus 1, combined with a base case in mathematical induction, Pn is always true. So I've got a whole new problem now, which is to prove this. Well, if someone just handed me this on a sheet of paper and said, prove this, I would have no idea what to do. But we have one important thing that we already know is true. We know that this is true. And so I'm going to write down what we know up here. This is still my ignore section. We know the following. We know this. And we're trying to show that. Well, you know, we've got a pretty good start on it. We're trying to show something about this big, long expression. Well, we've shown something about this part of it. We know that this part of it is equal to that. And so this is just kind of a desperation move. I'm just going to add this term to both sides of this expression. I'm going to add n plus 1 times n plus 1 factorial. And I know that's equal to n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial. All I've done is add this thing to both sides. So I'm going to go ahead and put that into my proof. And my reason is, you know, add same thing to both sides of 2. Alright, so going back to my ignore me section, my work area, right? I know that this is equal to that. What I'm trying to show is that this is equal to that. So really, what I'm trying to do is show that this thing is equal to this thing. Written in invisible ink. Trying to show that this thing and this thing are the same. Everyone with me? Thank you. Awesome. So we started with our inductive hypothesis. I wrote down what I was trying to prove and made the observation that I can turn this into something that looks like at least part of what I'm trying to prove by just adding n plus 1 times n plus 1 factorial to this side. To preserve the equality, I also have to add it to the other side. So I know that this is a true statement. I'm trying to show that this is a true statement. So all I have to do is somehow show that this is equivalent to n plus 2 factorial minus 1. So I've got a new task in front of me now, right? Show that n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial equals n plus 2 factorial minus 1. And a good time for a sanity check. So let's sanity check this. Let's set n equal to 4. So n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial. Well, if n is 4, this is 5 factorial minus 1 plus 5 times 5 factorial. So 5 factorial is 120 minus 1 plus 5 times 120. This is going to be 600, 720. This is going to be 719. And I want to show that that's equal to n plus 2 factorial minus 1. Well, if n is 4, n plus 2 factorial minus 1 is 6 factorial minus 1. 6 factorial is 720. That's going to be 719. So at least for plugging in one sample value, n equals 4, this formula seems to be correct. If I got different numbers, I'm going to give up. I'm going to, go study literature or something. But this seems to work, at least in this case. So we're going to forge ahead and we're going to see if we can actually prove this. Because plugging in one number and seeing it's equal doesn't prove it. So, this side over here is pretty simple. It's a factorial minus 1. We can't do a whole lot with this. But this, we've got a bunch of stuff in here. And the thing that's catching my eye right now is I've got an n plus 1 factorial and I've got an n plus 1 factorial. And I've got some things I can multiply by. There's an n plus 1 times this, and I've got a minus 1 that's just kind of sitting there, but I've got a minus 1 over here too. So I'm going to start doing some rearrangement on this. So I'm going to do n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial. Now remember, to show two things are equal, I can't manipulate both sides until I come up with an equality. That's not a proof, right? If that was the case, I could prove 1 equals 2 by multiplying both sides by 0 and saying 0 equals 0. So I can't modify both sides, but I can modify one side until it looks exactly like the other side. So I'm going to start modifying this. I'm going to leave my n plus 1 factorial. I'm going to leave my minus 1. But I'm going to multiply this thing by n plus 1. So I'm going to get n times n plus 1 factorial. And I'm going to take 1 times n plus 1 factorial and get an n plus 1 factorial. And now I'm going to rearrange some of my terms. I'm going to keep my n times n plus 1 factorial. I've got an n plus 1 factorial and an n plus 1 factorial being added together. That's going to give me 2 times n plus 1 factorial. And then I've got my extra minus 1 at the end. And now I'm going to combine terms. I've got n times this plus 2 times this. That's the same as n plus 2 times n plus 1 factorial. And there's my minus 1. And now we're going to use that observation that I made for you a few classes ago, which was this idea that, x factorial is x times x minus 1 factorial. This says multiply all numbers up to n plus 1. And if I do that and I multiply by n plus 2, that's the same as multiplying all numbers up to n plus 2. So n plus 2 times n plus 1 factorial is just n plus 2 factorial. And there's my minus 1. And I've done what I set out to do. I've shown that this thing is equal to that thing. So now if I go back to my actual proof, I can take this, I could reproduce all of that work over here, and I could show that this is equal to n plus 2 factorial minus 1. Right, so I would reproduce all this work in here. And now I've just shown p of n plus 1. And that follows from 3 and definition of p of n plus 1. Therefore, Pn implies Pn plus 1. Therefore, Pn for all n bigger than or equal to 1 by mathematical induction And that's what we were trying to show. So the most important part of this particular question is the setup. It's clearly defining a family of propositions that correspond to what you're trying to show, stating what it is you're trying to prove in terms of that family, stating a base case, demonstrating that the base case is true, stating the inductive hypothesis, and then at least getting down this far, right? And then you've got to do some gymnastics with factorials to be able to get down to this. But the majority of the induction related work is the setup, right? It's all of this stuff. And then if you play around with it and you do some stuff like this and this, right? Then you can get to showing that this sum is equal to that, and that's Pn plus 1. And then once you know Pn plus 1, you state the inductive hypothesis is true, you combine that with the base case, wave your hand and say mathematical induction, and then you've got Pn is true for all n. You will probably not see a factorial induction question on the final.
I appreciate that.
Mm-hmm. Trust me, so do I. All right, other questions on the homework?
Maybe the last one.
N squared bigger than 4n plus 1? N squared or 2 to the n? I think I wrote it down wrong. No, n squared, that's right. Is that the one? Yes, no, maybe.
Yeah, that's the one.
Okay, thank you. I don't have the assignment in front of me, I just have the notes I used to make it. All right, so again, family of propositions. So let's prove this for all n bigger than or equal to 5. So case 1 is the base case, step 1 is the base case. Let's prove p. Well, we're not going to prove p of 1 because we're not trying to show this for n equals 1, but we want to show it starting from n equals 5. So our base case is going to be p of 5. So p of 5 says 5 squared is bigger than 4 times 5 plus 1. And this is true. We can pop it into a calculator or an abacus or whatever, and this will be 25 and this will be 21. Okay, so inductive step, prove p of n guarantees p of n plus 1 as long as n is at least 5. So step 1, p of n, that's the hypothesis. Step 2, n squared is bigger than 4n plus 1. That's what p of n says. All right, so we'll go back to our ignore section. All right, so don't grade this. We want p of n plus 1. So we want to show that n plus 1 squared is bigger than 4 times n plus 1 plus 1. Right? Don't put this in your proof. If I write this down, my proof is done, and it's a low grade, right? We don't know that this is true. This is what we're trying to show, but we're writing it down on this, ignore section because we're thinking out loud. You don't have to include this in your proof. You can do this on scratch paper or whatever. We're trying to show this. Well, let's expand this we want to show n squared plus 2n plus 1 is bigger than 4n plus 5. If we can show this, then we can say, therefore, n plus 1 squared is bigger than 4n plus 1 plus 1, and that is Pn plus 1. And then we're done. Well, we want to show this. What do we know? We know n squared is bigger than 4n plus 1. So these inductive proofs are almost always a question of, I know something, I'm trying to show something. How do I go from what I know to what I want to show? And in this case, it's an inequality, but I'm looking at the left side, and, this is like this thing with a little bit of stuff missing. Or if I add a little bit of stuff to this, I get that. If I add a 4 to this, I get that. And so you play around with that a little bit, and you come up with this idea of, like, if I can show that 2n plus 1 is bigger than 4, then this thing plus 2n plus 1, which is this, would be bigger than this thing plus 4, which is that. And this I can do pretty easily because I know what? I know n is bigger than 4, so 2n plus 1 is bigger than 9, which is certainly bigger than 4. So now I can turn all of that into a formal proof. So 2n plus 1 is bigger than 9, which is bigger than 4, and this is because n is bigger than 4, right? We're trying to show this for n bigger than or equal to 5. So if n is at least 5, 2n plus 1 will be bigger than 2 times 4 plus 1, which is 9, and that's bigger than 4. And now I'm going to add this to the left side of this, and that to the right side of that. And so I'm going to say n squared plus 2n plus 1 is bigger than 4n plus 1 plus 4. And this is basically following from 2 and 3. And this is equal to 4n plus 5, which is equal to 4 times n plus 1 plus 1. And I'm going to rewrite my left side as n plus 1 squared and show that that's bigger than 4n plus 1 plus 1. And that follows from 4, and this is algebra. But I'm done, right? P of n is the proposition that n squared is bigger than 4n plus 1. N plus 1 squared bigger than 4n plus 1 plus 1. That's P of n plus 1. Therefore, P of n implies P of n plus 1. Therefore, combined with the base case in mathematical induction, P of n is true for all n bigger than or equal to 5. So usually, induction questions on the exam are going to be things like, adding consecutive integers, adding odd integers, postage stamp questions, things like that. They're usually not going to be things that involve, factorials or bizarre properties of logarithms or, tiling floors or identifying horses by colors or some of these weirder things that we've talked about, right? They're usually going to be fairly straightforward in that they're not going to require original insight in how to sort of get from, P of n to P of n plus 1. It'll usually be something we've done before in class. So if you review the examples we've done in class, right, you should be fine for induction questions on the final. All right, other questions? All right, back to counting then. So our next property is called the pigeonhole principle. And everyone knows what pigeons are, right? There's not a lot of pigeons around town, but where I grew up there was. Pigeons, you know, they're these birds that are trainable. And among other things, you can train them to fly very specific places. You can train them to fly from point A to point B. You let them know there's good food at point B, and when you release them from point A, that's where they'll go. And so pigeons have been used, you know, for sending messages across cities. You put a little message and you attach it to the pigeon's foot, and you send it to, you know, the remote pigeon office, and you can get messages delivered like that. And so people who raise and train and use pigeons like this, typically these pigeons roost in these boxes. And so you'd have, you know, like a wooden box with a bunch of compartments, and there might be, you know, 12 compartments or 12 boxes. And the pigeonhole principle is this following simple observation. If you have, you know, 12 or fewer pigeons, they can all roost somewhere in this structure without having to double up. But if you have 13 or more pigeons, and they all want to roost in this structure, at least 2 of them are going to have to share. Okay, that's the whole synopsis of the pigeonhole principle. And that's why it's called what it's called. So if you have 12 boxes and you have 13 birds who are going to occupy those boxes, at least one box is going to contain at least 2 birds. And it could be that, you know, all 13 birds are really friendly and they all gather up in one box. That does not violate this principle, right? All that this rule is telling you is that if there's at least 13 pigeons and there's only 12 boxes, at least one box will have 2 or more birds in it. All right, so we can make that sound a lot less interesting by using some mathematics. So if k is a positive integer, and k plus 1 objects are placed into k containers, or boxes, at least one box has 2 or more objects. Inside it. So k plus 1 objects going into k boxes, at least one box will have 2 or more objects. Does that make sense? Like intuitively, does everybody believe that? Does anybody not believe it? If we were in person, I'd be handing out like SpongeBob dollars for answers right now. All right, cool. All right, so this is a really simple principle, right? But we can do some surprising things with it. So, for example, if you have 27 names made out of, you know, letters from the plain old, you know, English alphabet, if you have 27 names, at least 2 of those start with the same letter. Arnie, Betty, Craig, Danny, right? You can name 26 names that don't repeat the first letter, but if you have a 27th name, it's going to repeat the first letter of at least one other name. And that makes sense, right? Because there's only 26 letters, and so how could you have 27 names that each start with a different letter? But we could prove this by invoking the pigeonhole principle. And what we would do is we would make 26 boxes, and we would label these boxes A through Z. And we would place each name in a box according to the first letter of the name. And we have 27 objects going into 26 boxes. The pigeonhole principle guarantees at least one box contains 2 or more objects. Those objects are names, and whichever box contains at least 2 names, those 2 names both start with the same letter associated with that box. And that proves this assertion is true. There's at least 2 names that start with the same letter. So it's a pretty obvious intuitive principle, but it gives us a way to more rigorously prove certain assertions without having to say, well, just look at it, you can see it's true, right? So we can invoke the pigeonhole principle that way. If you have 8 people, any 8 people, at least 2 were born on the same day of the week. Make 7 boxes, Sunday through Saturday. Put each person in a box based on the day of the week they were born. You've got 8 objects going in 7 boxes. At least one box will have 2 or more people. Those 2 people have been born on the same day, whichever day that box corresponds to. All right, your homework assignments are worth 20 points. And so there's grades of 0, 1, 2. There's 21 possible grades. There's 24 students in the class. You're guaranteed on every homework there's at least 2 students who got the same grade on the homework. No way around that. How do you know that? The pigeonhole principle tells us that with just 22 students, we can put them into one of 21 boxes based on the grade they got on the homework. 22 objects going into 21 boxes, at least one box will have at least 2 students in it. So just picking out any 22 students, at least 2 of them have gotten the same grade on the homework. And then there's 2 extra students, so, it just becomes more true. So these examples are not very startling. You may have thought of them on your own before, or, could think of them. How many different grades are possible, right? So enough people, you're going to have repetitions and so on. Let me wrap up here with a less obvious example, and this will use some number theory stuff, and this is a kind of cool fact. So every positive integer has some multiple that can be written in decimal using only 1s and 0s. Every positive integer has some multiple that can be written using only ones and zeros. Alright, what does that mean? Well, the number 1 is, you know, a number written with just a single 1. So that's fine. 2 times 5 equals 10. There's a multiple of 2 that's written with just ones and zeros. So that's doable. What about 3? Is there a multiple of 3 that can be written with just ones and zeros? SpongeBob dollars.
Yeah, I think 1.
3 is not very obvious, but one example would be 3 times 37 is 111.
Yeah, it was either 101 or 111 that I was thinking of.
Yeah, 101's prime, unfortunately.
That's what I figured.
What about 4? Is there a multiple of 4?
I mean, 1,000 is definitely.
Yeah, we could do 4 times 250.
Or 100.
That's 1,000. Or times 25. What about 5?
10, 100.
Yeah, 5 times 20 would be 100. So there's this interesting fact that we can always do this, right? So, you know, 6, I don't know, probably some version of 37. So 6 times 185 will give us 1110. But how the heck would we prove that we can always do this? And what does this have to do with pigeons? And so here's an example of how we can restructure a problem in terms of objects and containers and then sort of wing the pigeonhole principle at it and find a solution. Alright, so start with n. Which is some positive integer. Alright, so consider the n plus 1 numbers. 1, 11, 111, 1111, and so on. N plus 1 numbers where each number we're considering consists of just that many ones side by side. Alright, so take these n plus 1 numbers, look at each number modulo n. So we want to find a number between 0 and n minus 1 that each of these is congruent to. And we're going to form a series of bins. This first one I'm going to call congruent to 0, this is congruent to 1, this is congruent to 2. The last one is going to be congruent to n minus 1. So we have a total of n bins, and I have n plus 1 numbers. And I'm going to start putting these numbers into bins based on what they're congruent to modulo n. I have n plus 1 numbers, I have n bins. What does the pigeonhole principle tell me? At least one bin will contain 2 or more numbers. Alright, what do we do with that? So at least one bin has 2 numbers in it. Could be more than 2, but it has at least 2. Well, those 2 numbers are going to be in the form, you know, big bunch of 1s and something with a smaller number of 1s. Right? Every number I put in the bins is a succession of 1s. So if I pick a bin that has two numbers in it, one of them will look like this, one of them will look like that. And if I subtract them, I will get a number containing a bunch of ones followed by a bunch of zeros. That's a number in the required form. Well, since both of these numbers were in the same bin, it means they're both congruent to the same thing, modulo n. If two numbers are congruent modulo n, their difference is a multiple of n, which means n divides this number consisting of just ones and zeros. So there is a number consisting of just ones and zeros, which is a multiple of n. And that's what we're trying to show, is that starting with some n, we can find a multiple consisting of only ones and zeros. And so that tells us we could find, some multiple of 7 consisting of just ones and zeros. And that's, I don't know who came up with this first. To me, that's a horribly clever application of the pigeonhole principle that I would never have thought of in a million years. But it's a nice illustration of, this sort of obvious seeming property that if you put too many things in too few containers, you're going to have, you're going to have to double up. We can apply that to this very unlikely result that we can always find a multiple of any number that can be written as just ones and zeros. The other thing is, this is not really a constructive proof. It doesn't tell us, what that multiple is. It doesn't tell us what the thing containing ones and zeros will look like. It just proves that such a number exists. But we could use this to, find a multiple of 7 that can be written with ones and zeros. At most we have to do 8 calculations. So let's just wrap up with that. So we're looking for a multiple of 7, so we're working mod 7. So 1 is just congruent to a 1. 11 is congruent to 4, it's 4 more than 7. And I'm going to cheat and use my calculator here. So 111 is going to be... So here's what I'm doing. I'm doing 111 divided by 7. That gives me 15 point something. So I'm doing 111 minus 15 times 7, and that gives me a 6. And then 1111 divided by 7 is 158. 1111 minus 158 times 7, that gives me a 5. And then 5 ones is 1587. This is going to be congruent to 2, making me work for this. This thing is, well, this thing itself turns out to be a multiple of 7. So that's congruent to 0. But let's go ahead and do the pigeonhole principle. Let's do 7 ones. So 158, 730. So this is congruent to 1. And so we've got, we only did 7 numbers, and we already found a duplicate. So these two numbers are congruent to each other, modulo 7, which means their difference. This should be a multiple of 7. If we take that and divide it by 7, we get an integer. So there's a multiple of 7 that's expressible as just a string of ones and zeros. And that demonstration using the pigeonhole principle says we could do this for any number. right? We can pick any number n and find a multiple of it that we can write as, in particular, a string of 1s followed by a string of 0s. All right. So I'm not going to have homework due next Wednesday. I will post homework on Monday, and probably make it due the following Monday, because we missed a class this Monday. So no homework to start on yet, but I'll post some homework on counting over the next few days. Monday we'll finish talking about counting, and that'll let you get started on your homework. And then we're going to switch and start talking about automata theory. We're down to 4 classes left for the quarter, so we'll spend probably 2 classes talking about automata theory, and then probably the last 2 classes talking about some graph theory, and then some wrap-up for the final. So coming up to the end of things fast. All right, so we'll continue with pigeonhole principle and talk about permutations and combinations on Monday, wrap up counting, and then move on to automata theory. All right, that's all I got. Have a good one. I will see everybody next time.
Thank you.
Thanks.
Thank you. Have a good day.
You too.